Hello everyone and welcome to Valiant Tech World. Today we're going to talk about polynomial regression. We will start by describing a problem, then we will show how this problem can be solved with polynomial regression. We will evaluate the results and then discuss the solutions found. Imagine that in a distant future, the robots become intelligent enough to be able to create spaceships and go and explore the universe. They are interested in understanding the universe, but more practically, they also need to find resources in other planets to expand their colonies and improve their technology. So, they organize missions where they try to find new planets which can have metals or minerals of interest that they can extract. Suppose that during one of those missions a new potential planet is found, and the scouts decide to land on the planet to better understand if there are relevant resources. After the landing, the robots start to inspect a promising area, but unfortunately one of them falls into a pit because the ground is not stable everywhere. Now this scouting mission becomes a rescue mission. The blue robot goes cautiously near the hole and sees the yellow robot. It requests help from the main spaceship, but they want to know the height between the blue robot and the yellow robot in order to select the best rescue plan. The blue robot does not know how distant the yellow robot is. However, it remembers that it can use an old device to calculate the gravity of the planet, and then can use this value to calculate the height. This device, similar to a ball, calculates the time from the moment the robot let it fall to the moment it touches the ground, and then transmits it to the robot. Also, the robot has some sensors that allow to calculate his height from the ground, but they cannot be used for the pit because it is too deep. So, the robot repeats these experiments several times, and every calculated time from the device is associated to a specific height calculated from the sensors of the robot. In this other example, the robot climbs a large rock and repeats the experiment, but this time it obviously takes longer to fall given the increased distance from the ground. By the way, the green rocks are some of the minerals that the robots are looking for, but at the moment the main focus is to save the scout. We can see overall the landscape, and the robot tries to use every available rock to gather as much data as possible before trying to make a prediction. The amount of data is important to improve the accuracy of the predictions. The table shows that the relationship is overall quadratic, and this is expected and in line with the free-fall formula. So the polynomial regression is selected and the data will be used to calculate the required coefficients. Before going into the details of polynomial regression, here it is a brief explanation of the free-fall formula. In practice, the height of an object in free fall is calculated by multiplying the gravity with the square time to reach the ground and divide this value by 2. So, by knowing several heights and their associated times, we can then calculate the coefficient g, which will be the gravity of the planet. Remember that the formula is an approximation which does not take into account of other factors such as wind, air resistance and so on. But for this example we can assume that the planet does not have much air and all these factors can be considered overall not too disruptive. Now let's see the formulas for the polynomial regression. They are similar to the ones used for the linear regression. But while in the case of linear regression there is a single feature associated to a certain coefficient, here you have the same feature repeated multiple times but with a different exponent, such as x, x squared, x raised to the power of 3 and more generally x raised to the power of p. We are showing an example where there is a single feature with different exponents. This can be generalized further by adding other features, but overall the math is the same. Note that the equation is still linear in the coefficients. We can summarize all the polynomial terms in the matrix x, and then we can use ordinary least squares to find the vector beta similarly to the linear regression case explained in previous videos. So, the problem can be solved by using ordinary least squares, where the sum of all the squared differences between the predicted and the actual values are minimized. The aim is to find a vector beta with all its p plus 1 coefficients, where p are the coefficients related to the p different exponents of the only feature considered, and then there is the intercept. The solution can be found by using the same formula used in linear regression problems, and for more details about linear regression I have done several videos with examples, explanation of the math, and some of the metrics typically used in regression problems. If you are interested in this topic, you can find these videos in the description below. The polynomial regression problem can be evaluated with regression metrics. These are the formulas of common metrics used in regression problems. These formulas provide a single number which tells how good the function fits the data, because they take into account the different epsilon differences between the actual values and the predicted values. Smaller number is associated to smaller difference and overall better fit, and the best possible value is 0 for all these metrics. Another metric that can be used for polynomial regression problems is R-squared. The metric is typically used for linear regression problems, but given that the problem that we are solving is still linear in the coefficients, it can be used for this case as well. R-squared provides value typically between 0 and 1, where 0 is the worst and 1 is the best, and tells the proportion of the variance of the dependent variable that is explained by the independent variables. So, if the inputs can explain most of the output, then the value approaches 1. Otherwise, if this is not the case, the value goes towards 0. As I said before, I have done a video on regression metrics which provide more details and examples on all these formulas. You can find it in the description below in case you are interested. Now we know the formula that we need to use to calculate the coefficients, and we have the time calculated by the device for each drop as an input and the related height as an output. We can see that the free-fall formula is a specific case of the equation shown before with p different exponents and the intercept. In this case, there is no intercept and there is only a single coefficient, which multiplies the input x squared. And that input is the time, and the output y is the height. We are trying to find a single value beta which will be equal to the gravity divided by 2. Once we know this coefficient, we can drop the device into the pit, and we can use the transmitted time to estimate the height, which is roughly the distance between the blue robot and the yellow robot. Let's drop it then. Well, it did not go exactly as expected. It seems that there is no robot to save anymore, so all the calculations, formulas and experiments were done in vain. So this concludes the rescue mission and the explanation. Bye. That was a joke. These are very advanced robots, and they should be able to drop the device without hitting the other robot. By the way, if you are enjoying the video until now, please click the like button and subscribe to this channel. Now, let's try it again. Better. So, the robot used all the experiments to get an estimate of the coefficient beta, which is half the gravity, and now the robot will use this coefficient with the transmitted time from this last drop to get an estimate of the distance from the yellow robot. Let's show some results. The orange points are all the experiments done by the robot to train the model and find the gravity, which is 2 times beta. In this test, we set the gravity of the planet to 1. The points are not exactly on the green estimated curve because there are small errors which are not taken into account in the formula, such as the atmospheric factors mentioned before. However, overall the estimate of the gravity shows that it is close to the real value, and root mean square error is small given that we are considering heights of tens of meters, and R-squared is really close to 1. Before dropping the device into the pit, the robot also uses testing data. These are experiments not used to find the gravity, but if the estimate is accurate, the points should still be close to the green curve. And as we can see, Also in this case, the curve is able to describe the points pretty well, and both the root mean square error and R-squared are close to the values obtained for the training data. We do not have points roughly over 40 meters, so we are assuming that whatever depth the hole is, the function will still be quadratic and well described by the estimated coefficient. This is not always the case, but in this simple example we can assume this to be true. As shown before, the blue robot drops the device and the device transmits back 12 seconds, which, by using the estimated gravity and the freefall formula, provide the answer we were looking for. The distance between the two robots is roughly 70 meters. And now the blue robot can send this information to the spaceship to save the yellow robot. Let's do one more step. We can increase the number of coefficients by taking into account other factors that can influence the final result. Let's assume that the robot, instead of dropping the ball, launches it upwards always with the same speed. If this is the case, it is an important factor that needs to be taken into account, given that the device is not only influenced by the gravity of the planet, but also by the initial speed. We can modify the freefall formula by adding the term related to speed, which is simply multiplied by time, and not by the time squared, like the gravity. So now we have two coefficients, like beta 1 and beta 2, but no intercept beta 0. Note that the value assigned to the initial speed is minus 0.5, and it is negative because the device is going upward, and it is opposite to the gravity, which moves the device downward, and we are considering positive. We can again use linear regression formula to find these coefficients, and also in this case, the estimates are close to the actual values, and the metrics are also similar to the values of the other cases. By having a more general example, it is possible to check what's going to happen to the height in case the device transmits 12 seconds. If the device goes up and then down, it wastes some time before it changes direction and begins to fall and then touch the ground. This is translated into a smaller height. In this case, with speed set to minus 0.5, the initial speed is not too disruptive, and the result is similar to the case where there was no initial speed. We obtain roughly 65 meters instead of 70. We can see from the 3D plot that if we set the speed to more negative values, then the height decreases because the device takes more time to change direction and fall, and then touch the ground. On the other hand, if the initial speed is set to positive values, the height increases because it means that the robot is essentially throwing the device downwards with a certain speed, and not just letting it fall, so the device will be able to cover more distance in 12 seconds. In our example, we used a quadratic function, but as said before, polynomial regression works with polynomials of any degree, as long as you have enough data to get a good estimated curve. You can see in this other example that the linear regression is certainly not describing the data well, and also the polynomial regression with only quadratic or cubic terms are not providing particularly good results. On the other hand, with fourth degree polynomials, now we have a function that is closer to the data points. Sometimes you might want to test different polynomials in order to find the most useful for the problem that you are trying to solve. This concludes the video, and the robots were able to safely leave the planet. And if you enjoyed it and found the content useful, please click the like button and subscribe to this channel. You never know, one day math might save your life too. Thank you for watching.